is to very short presentation of how to use ROS in combination with the Webots software, which is a simulation software. So first, a list of topics. I will explain you briefly what is Webots, then how to use ROS in combination with Webots. So I will mostly explain this topic. And to exemplify the use of ROS inside the Webots software, I will take a very basic example of joysticks or hardware joystick plugged to your computer, which will act on a simulated robot, simulated in Webots. That's what I will do. So first, what is Webots? So it's environment development where you can model your robot first, then you can program it, and of course, simulate it. So it is mostly used in research, education, but also industry. So there are over 1,000 universities and research centers that are using Webots right now. So provided with the software, you have a very complete technical documentation. You have a support service directly from the developers of Webots. You have also forum for users and a set of tutorials. So what I'm going to do, what I'm going to talk to you within the few minutes to come is a part of a tutorial which will be available soon on the web page. So although it's non-free software and non-open source, all the models, all the programs inside the distribution are available for you. Therefore, they are under the BSD license. So let me summarize the key features of this software. So first, it's a cross-platform. So Mac, Windows, Linux. You got them? You can choose your favorite programming language. So maybe most relevant to us today is C++ and Python, because if you use ROS, you are using C++ or Python. But you can also use Java and MATLAB. So it's a real-time physics simulation in the sense that physics is simulated and it's always aiming at real-time. So all the provided examples in distribution are running real-time and above. But depending on the complexity of your system, you may be not able to reach real-time. You, for some robots, can remote control your robots from the Webots software. And you can also cross-compile your compiler. So it's possible, for instance, for the Epoch or the Robotist Day1 OP. And a strong point of the software is also that you can build your robot from a quite handy graphical user interface. So you have copy and paste capabilities. Then you are adding nodes, you are stacking nodes. So following a tree-like structure, you are adding your components. So a body, say a body, then a joint, then a body and joint, and so you are building robots and adding devices, and you pick the devices into a rich library of ready-made objects. So ranging from bumpers for sensors to LiDAR-stick sensors or, I don't know, spherical cameras, for instance. And all these devices, which are simulated in Webots, you can turn them into a ROS node. So this, I will explain it later. So it is ROS enabled in the sense I am going to explain. And what I can say now is that there are several projects which are using Webots in combination with ROS. So I know that in the German University of Australia, there is a Webots KUKA U-bot model, which is controlled by a ROS controller. And researchers at the SAI Institute are also using a Landshark model controlled by ROS. So it's working. So here are a few robots simulated in the software. So Robotist Day1 OP, Aldebaran's Now, Adept Mobile Robotics, Pioneer 380. And here is an overview of the software. So let me briefly say what we see. On the left side, you have what we call the scene tree. This is where you design your robots, and you see most of the characteristics of your simulations. So the positions. On the center, the 3D view, so That's where you run your simulation. You have basic 3D navigation tools, but you can also interact at runtime by adding a force or torque to your robots, objects. And in the next release, you will be able also to resize objects at runtime. And on the right, so most prevalent for us today, is the programming interface, so a build editor with highlight syntaxing and jump to error capabilities. And you can here program your C controller, your C++ controller, or Python controller here. Here it's just the basic things about Webots you have to know. So when you are working with Webots, you are working on a project. It's a directory, and it contains at least 2 other directories. The first one, called words, contains the word files. So that's the files that are describing the environments your robots are sharing. So you define using an extension of the VRML language, so virtual reality markup language, the world and the robots you want to use. So it's not URDF, but maybe later we will implement an importer. But it's quite human readable and useful. Then you have the controllers directory, and inside it you program your controller files. So controller in Webots word is just an executable file that will drive either simulated robots or real robots from the software. Okay, and now I explain you how to use ROS inside Webots. So basically, what we have to do is just to implement a Webots controller as a ROS node, possibly connected to other nodes. And so inside the controller source file, you use first the Webots API functions, and then the ROS API function to publish on the desired topics. So very straightforward examples. So for instance, if you want to publish a camera image, then you get this image with a Webots API function, and you can turn it very easily into the corresponding ROS message. That's under the format of int8 multi-array, for instance. Okay, so it's a really simple 2-step process. First, we generate the ROS executable using the ROS build system. And then we copy the executable at the right place. That means where Webots expect it, so in the control directory. That's what you have to do to set up your project. Now I go a bit further into the details. So my example is the example of a single controller called joystick. So it reads the output values of a real hardware joystick plugged to your computer, and transforms them into motion commands for a simulated robot. It will be a simple differential with robots. So what we've got here, so it's the joystick controller will be a ROS node, and we have to implement it, and it will subscribe to the main topic of the joy node, called joy, and listen to the axis and the button values. And the joystick also will launch the joy node. So the joy node is already present in ROS distribution, it's not new. And by means of ROS launch, so in a launch file, it's quite standard stuff. So here I'm going to rebuild the whole project you need to make the simulation work from the bare bones. So what are the bare bones? So first, the description of your world. So your environment and your robots here in the world file. Then the source file of your controller. So I choose here a CPP extension file. And then we also need this launcher file, which is quite straightforward. So in the source file, you have to add first the ROS headers, okay, for the joy node. Then the Webots headers, so we will be simulating a robot which is a differential wheel, that's why we need only these 2 headers. And then inside the code, you launch the joy node with the ROS launch program. So using the launcher defined earlier. So, and the main instruction we see in this controller is that we subscribe, so at frequency 10 Hz, to a callback So we subscribe to the joy topic, and at frequency 10 Hz, we are calling a joy callback, which will read the value along the axis of the joystick and on the buttons, and turn it into a robot motion by setting the speeds of the wheels of the differential wheels. So we grab the values from the joy node and set them using the API function from Webots called set velocities. Oh, for this. Okay. Now, concretely, how do we build such a project? So first, we create a Catkin workspace inside the Webots directory. So here, these lines are excerpt from the ROS beginner tutorial. It's pretty standard. You create a directory and you init it with Catkin command. Then inside this Catkin workspace, so Catkin is the official ROS build system. Then you create a package with the command catkin create package with the arguments, the name of the package, Webots joystick, and two dependencies, which are the obvious one. So we are implementing a CPP controller, and which depends on the joy node. So we specify these two dependencies here. And when we did that, there was a file, a CMake list file that was automatically generated here in the package, and you have to append a few lines to link the executable to Webots controller library. So here we add always the same 4 lines to the CMake files. Then we go up in the Catkin workspace, tap make, essentially, and we are done. What remains to be done is just to copy the executable, eventually, possibly rename it inside the control directory. And that's it. So, a summary of what we did. First, we create a Catkin workspace inside the Webots control directory. And inside this Catkin workspace, we created a ROS package called Webots joystick. And that's pretty much it. So all the detailed instruction can be found on the website. There is a tutorial explaining how you can set up your ROS node inside Webots. And what I did with the joystick, you can do it with all the simulated devices that you can find inside the Webots software. So thank you very much for your attention. That's the end of my talk.